So, with all of that, where does resistance come from? And especially, where does acquired resistance come from? Well, it is a natural phenomenon. Resistance is oftentimes a byproduct of something else. We can think about many of our organisms being produced by soil organisms. And so, bacteria that live in the soil are surviving in an environment that contains antimicrobial compounds, and they need strategies in order to do that. We have enteric organisms which survive in the gut in the presence of bile acids, and they may have adapted efflux pumps in order to expel those really toxic compounds. Not only is resistance natural, but it's ancient. It's been around for a long time. And I think this was really nicely exemplified by this letter to nature by the Wright Group out of McMaster University in Hamilton, Canada, where they identified beta-lactam and tetracycline resistance from samples of 30,000-year-old Beringian permafrost in the Yukon and northern British Columbia. So long predating the introduction of antimicrobials to clinical use. So resistance to every drug that we have or will ever use in the future already exists. The clinical issue arises when we select for it. And we select for it by using antimicrobials. So any drug use, whether it's appropriate or inappropriate, will apply a selection pressure and encourage the organisms to become resistant. So what I want you to take away from this is that if you use a drug, it better be worth it. Certainly, inappropriate antimicrobial use is the low-hanging fruit. It provides potentially no benefit for our patients and yet still applies this selection pressure. But appropriate use of drugs also applies this selection pressure. So we really need to be careful how we use these tools and ensure that they're being used as judiciously as possible. Bacteria adapt very quickly. They have a tremendous amount of evolutionary power. And I think this is sort of an interesting thought experiment. So if we consider how many generations we have had in our history as a species, if we say Homo sapiens have been around for maybe approximately 750,000 years, with a generation time of 25 years, that gives us 30,000 generations, give or take, in our history as a species. If we think about bacteria, in the 82 years since the introduction of antimicrobials, with a generation time of 20 minutes, we have over 2 million bacterial generations. And when we consider that bacteria don't rely on sexual reproduction for genetic diversity, it's little wonder that they've been able to adapt so quickly to this new selection pressure we're applying to them. So how do bacteria actually become resistant? Where does it come from? Maybe the easiest to understand is mutation. So here we have a bacteria, a susceptible bacteria, and a little snippet of its genome. You can see our nucleotides here, our A's, T's, G's, and C's. And as that organism is dividing, sometimes a mistake is made in DNA replication. So in this case, we have a T to a C, and this happens to occur at a location which impacts how an antimicrobial will impact the organism. We can have a process called conjugation, where a resistant bacteria on the left here can share its resistance genes with a susceptible organism. These are called resistance plasmids, these mobile genetic elements which can contain resistance genes. And then its friend over here becomes resistant. It expresses that gene and displays the same phenotype. We can have transduction. So bacteria can get infections with bacteriophage. Sometimes as phages replicate, they can take a little bit of extra DNA from the host along with them. On the off chance that contains a resistance gene, that can then be transferred on to the next organism they infect. Or we can have transformation. So this is an organism acquiring exogenous DNA from the environment, picking it up, expressing it. If that happens to contain a resistance gene, then we have a transformed individual, which is now resistant. Now we're very briefly going to go through some of the mechanisms of resistance for the most important classes of drugs in veterinary medicine, starting with the beta-lactams. There's a few mechanisms that I think are important to understand. One are altered targets, so altered penicillin binding proteins. This is actually the mechanism of resistance that we see for our MRSAs and MRSPs, also for streptococcus resistant to penicillin, and Different penicillin binding proteins, so PBP5, is actually responsible for the intrinsic cephalosporin resistance among enterococci. Gram-negative rods, particularly our non-fermenters, are notorious for shutting down their cell membrane. They close off their porins and they simply don't allow anything in. This can lead to beta-lactam resistance as well as resistance to other drugs. And then we have beta-lactamases, degradative enzymes which are produced by many, many bacteria. We'll be exploring these in a little bit more detail in a future lecture because it's one strategy that you can actually do something about. So why is it important for clinicians to understand this? This all sounds very academic and like something that only microbiologists get excited about. Well, I hinted at it when I mentioned beta-lactamases. So there are some mechanisms that we can counteract with beta-lactamase inhibitors. Some bacteria produce beta-lactamases, which we can arrest using something like clavulanic acid or sulbactam. Knowing which bacteria do that, as compared to other instances where a beta-lactamase is not responsible for resistance, allows us to select the most appropriate therapy. So methicillin-resistant Staph aureus or pseudointermediates will never be effectively treated with amoxicillin and clavulanic acid because the resistance to beta-lactams is not due to the production of an enzyme, it's due to altered targets. Briefly, for the tetracyclines, we see efflux as a very common mechanism of resistance in both gram-positives and negatives. Interestingly, resistance conferred by efflux pumps is not necessarily across the entire class. So if you have a multi-drug resistant organism, it may be worth requesting that the lab test multiple tetracyclines in their panel. Potentially, you still have an option there. We see ribosomal protection. This is very common in Staph pseudointermediates as a result of TET-M. It results in a conformational change in the tetracycline binding site on the 30S ribosomal subunit that essentially prevents the tetracycline from binding. And then we can also have ribosomal mutations or enzymatic inactivation, which can confer resistance. Aminoglycoside modifying enzymes are one of the most important mechanisms of resistance, particularly in gram-negatives. So they enzymatically inactivate or alter these compounds. We also see decreased permeability. These are really large drugs and can have a hard time crossing into the cell when we have, for instance, porin deficiencies. Oftentimes, when we see decreased permeability resulting in aminoglycoside resistance, we also get cross-resistance to other antimicrobials. For our macrolide type drugs, we see ribosomal methylases, maybe most notoriously the family of genes. When we have the family of genes, you need to be aware of inducible resistance. Not all drugs will as efficiently turn these genes on in vitro. And so our susceptibility tests don't always reflect what happens in the patient. So if ever you see a number of different macrolides or macrolide type drugs on your panel, you have susceptible to some and resistant to others, it may be worth consulting with the lab to see if they've done some specialized tests for instance, inducible clindamycin resistance. We can also see active efflux and enzymatic inactivation. For our fluoroquinolones, there are a variety of mechanisms, including target mutations. So we can get single nucleotide polymorphisms or SNPs in the JAR-A and PAR-C genes, the DNA gyrase and topoisomerase. These can lead to sort of incremental decreases in susceptibility that can result in MIC creep over time. We can have active efflux, either through the MAR operon, which leads to multi-drug resistance, or increasingly we see plasmid-mediated fluoroquinolone resistance as a result of target protection. So it prevents the drug from binding to its site. The QNR family of genes, as well as QEP, are important examples. And then finally, our folate synthesis inhibitors. We can get resistance to sulfonamides through hyperproduction of PABA. So the organism produces more and more and more of PABA to essentially reverse or prevent the competitive inhibition of sulfonamide on dihydroxypteroate synthetase. Or we can have altered dihydrofolate reductase genes, resulting in trimethoprim resistance. In gram-negative bacteria, we also have the SUL genes, which are responsible for sulfonamide resistance, and these are oftentimes physically linked to other resistance genes in the chromosome or on the plasmid. So we oftentimes see this with multi-drug resistant organisms. But what about antimicrobial stewardship? What does this even really mean? This is a term that I think gets thrown around a lot, either stewardship or prudent use, evidence-based use, but I think we need to take the time to define what we're actually referring to. So in this paper from Gardabasi and Prescott, they define stewardship to mean the multifaceted and dynamic approaches required to sustain the clinical efficacy of antimicrobials by optimizing drug dose, choice, dosing, duration, and route of administration while mimicking the emergence of resistance and other adverse events, which I think is really critical, and we'll come back to that in a few slides. This is a definition from Human Infectious Disease, where they define stewardship as a coherent set of actions which promote using antimicrobials responsibly, translated into context-specific and time-specific actions. And I think this is really critical for veterinarians because we work in so many different contexts. An individually owned dog is going to be very different from a flock of chickens, which will be very different from a pen of Atlantic salmon off the west coast of Canada. And stewardship will also necessarily look very different in each of these scenarios. So what should antimicrobial selection be based on? Well, microbiologically, it should be based on the pathogen that's identified, or at least the likely pathogen, the susceptibility of the organism or knowledge of local resistance epidemiology, of course, the animal species, signalment, the site and type of infection, any comorbidities that are present, and then the route of administration. We also have a number of other factors which are important to consider as well. So drug cost, client compliance, is the person actually going to give the drug to the animal as you've prescribed them, the label indication of the drug, and the withdrawal time. So these are the ideal considerations, but we know that there's probably other factors which impact how drugs are prescribed. So this is a study, again, from the UK, where they looked at other things that influenced veterinarians in their prescribing decisions. One that came up were business factors. We recognize that veterinary medicine is a private industry and people are customers. And I think there's a recognition that clients oftentimes want antimicrobials. They may demand a prescription, and that if a veterinarian doesn't prescribe it to them, they can go down the street to the next practice where they may be very willing to write them that prescription. And if that happens, you've lost money, you've lost some income. People are also afraid. They're afraid for missing an infection. And I think this is where sort of just in case prescribing may come into play. And then, of course, they're afraid of having a client complain. So in this quote here, they said, vets are completely paranoid. The Royal Veterinary College is going to cause them damage or get them struck off. So they'll lose their license and not be able to practice. There's habitual practice factors. So people get used to practicing in a certain way. They get used to prescribing a particular drug for a particular presentation. And that habit sort of carves a deep groove in how they do their work. Interestingly, this is something that is less commonly seen in new grads. So this person reported the new grads are initially more prone not to give antibiotics because they were taught, well, that's actually bad, and they stand their ground more. But as they get into practice and get more experience, and maybe they just get worn down, or maybe the daily life, then they start giving antibiotics more loosely. So for all of you soon-to-be veterinarians who are taking this course, please keep this in mind. Remember that you are leaving vet school with the most up-to-date knowledge, and you can actually serve as a resource for your senior colleagues. And then finally, pharmaceutical factors. Veterinarians are marketed to, and we need to recognize that some of the characteristics of drugs that are marketed as beneficial, such as convenience of dosing, are not entirely in alignment with good antimicrobial stewardship. So it's important to always be mindful of what is a sales pitch versus what is actually the most appropriate thing for each patient. For future prescribers, I think it's really important to know the names of the drugs versus just the names of the brands. So this is a famous painting by Magritte. This is not a pipe, it's a picture of a pipe. Similarly, I think we can make the analogy that Baytril, this is not an antibiotic. This is a brand name. I think we as a profession really need to recognize the impact of marketing. How many of us only refer to a drug by its trade name and maybe don't even know what the active ingredient is? Understanding that active ingredient is really, really critical. We can have an intelligent discussion about what are the characteristics of enrofloxacin. It's a fluoroquinolone. This might be its spectrum of action. These are its pharmacokinetic properties. These are some issues associated with resistance with enrofloxacin. We can't really have that same in-depth conversation about a brand name. So knowing the active ingredient is absolutely essential. All of that being said, I think it is important to recognize that there's a lot of really useful information we can gain from pharmaceutical companies. It's just important for prescribers to critically evaluate the science versus sales. Selling these drugs is a business, and the information they provide you isn't solely for educational purposes. So if the emergence of antimicrobial resistance and the thought of all of the nasty things that potentially come with that isn't enough to get you to start thinking about changing your prescribing decisions, I'd like you to consider the more proximate risks of antimicrobial usage. Antimicrobials in people are responsible for a large number of adverse drug events. This is some information from the US Centers for Disease Control. On their website here, cdc.gov/antibiotic use. You can learn a lot more. But what they state is that antibiotics are responsible for 1 out of 5 emergency department visits for an adverse drug event. So very, very, very common. And antibiotics are the most common cause of emergency department visits for adverse drug events in children. So anytime you prescribe an antibiotic, not only are we potentially selecting for resistance, but you potentially are running the risk of an adverse drug event in your patient. So you need to have a solid justification for using that prescription. These are not 100% benign interventions. So just in case is really not a good reason to use antibiotics. Diving into this a little bit more, this was a paper from JAMA Internal Medicine. And what they looked at were the number of people in a hospital who had received antibiotics and had an adverse drug reaction. And what they found were that 20% of hospitalized patients who had been given antimicrobials had an adverse drug event. So 1 in 5, way more common than I think most people would realize. And perhaps more alarmingly, 20% of those adverse drug events, or 19%, occurred in patients who had no indication for the drug in the first place. So they had no benefit for receiving that drug. They only got the downsides. A couple of quotes from this paper that I thought were really germane. Adverse drug events are common among inpatients receiving antibiotics, some of which may be avoidable with more judicious use. And then next, antibiotic-associated adverse drug events may not be recognized by clinicians because adverse drug events have varied manifestations. And if this is true in people, a very homogeneous species, relatively speaking, I think we really need to consider that there's probably a lot of adverse drug events in our veterinary species that we also may not be recognizing. So to summarize all of this, what does stewardship mean to me? Number one, you need to treat a diagnosis, not a syndrome. So a dog peeing on the carpet is not a diagnosis of a urinary tract infection. It is an observation which warrants follow-up. You need to concatenate laboratory evidence and your clinical exam into that diagnosis. So a simple lab result is not a diagnosis in and of itself. You need to ask questions when you need more information, either from the lab or the client. Using evidence-based empiric therapy. So what are the most likely pathogens and what do you know about local resistance epidemiology, not simply shotgunning with broad spectrum polypharmacy. Applying your knowledge of intrinsic resistance, drug mechanisms of action, and spectrum of activity and mechanisms of resistance to every decision you make. Recognizing that the world of infectious diseases changes quickly. And I think we've all seen this in the context of the pandemic, but it certainly occurs in the bacteriological world as well. So resistance is emerging and you need to be nimble enough to adapt. So lifelong learning is critically important. It's a professional duty for veterinarians. And I think it's important to sort of come out and say that if you're not up to date, you're out of date. One really useful tool that you can use to stay up to date are recognized therapeutic guidelines. Here in Canada, the Canadian Veterinary Medical Association publishes these guidelines on their website. And if you're a member of the CVMA, you can access these. I also wanted to highlight this app here, First Line, which allows you to access the current CVMA guidelines on your smartphone. Finally, I think it's really important to be reflective of what the clinical outcomes we observe are and what we think ultimately led to those. So we're really, really good about attributing an outcome to something that we did, but that is not always the case. And I just wanted to highlight some possible explanations for discordance between a test result, so susceptible or resistant, and the clinical outcome. So, for instance, we can have an unexpectedly positive clinical outcome for pharmacokinetic reasons. Maybe the pathogen was found to be resistant by the lab, but because we get such high concentrations of the drug in the urine, we overcame that resistance and it was successfully treated. Unexpectedly negative outcomes could be due to situations like failure of a drug to penetrate a protected site. Maybe the infection is in the central nervous system, and that drug is labeled for a urinary tract infection. I'm not going to go through all of these, so if you're interested in going through this table, please just pause the video. And then finally, I have a few questions for self-assessment.